I'm John Howell, and what I'm going to cover today, I'm going to describe to you how to get interesting, rich desktop applications, word processors, photo editors, things like that, running in a really minimal environment. I'll show you how minimal, but I'm talking about microkernel scale, something much less complex than the Linux environment that they might have grown up in. Excuse me. Okay, so for this talk, I'll start by motivating why repackaging applications this way is a good thing to do. Then I'll give you a concise description of this narrow Picoprocess environment and just show you how minimal it is. Then I'll describe our core technique, which is emulating a small chunk of POSIX. And then I'll show you another technique that we use for packaging these applications called zones, where we take programs that are expecting to run as entire processes and treating them more as libraries inside an existing process. So let's take a step back. For the last 20 years, if there's one thing we've learned about sending untrusted code to clients, it's that we do that, we can isolate that code in the client using type safety. So we've used this basic technique with Java, kind of where it started. But we've also used it with Flash and Silverlight, and now very widely with JavaScript. And the idea is pretty simple. We can send this code down, and our adversary can do some interesting Turing-complete computation, all in the confines of this narrow type-safe environment. And it's easy to write an interpreter for that environment and be confident that you got it correct. Now, that's not the whole story, because this program that we're running and doing these computations needs access to the outside world somehow. So inevitably, we end up adding some class libraries to that environment so that the code can call out to Java classes or to JavaScript support functions to interact with the rest of the world. So let's go into a little more detail about how this thing looks inside in Java. In the Java world, the JVM actually has a pretty straightforward specification. You can go off and write a JVM interpreter and be pretty confident that you got it right and that you made it correct, and it can't be, it's not vulnerable to isolation failures. But of course, the first thing we needed to do when we had our Java programs running in our web browsers was we wanted to interact with the world. We wanted to have buttons and things like that. And so we got the abstract windowing toolkit. And the idea there was we had buttons in macOS, and we had buttons in Windows, and we had buttons on SunOS. Takes me back. And so these buttons were written in these native libraries. And what Java did is wrap them in a class library and said, oh, if you want to have buttons, your adversarial code can call this. And we just kind of tried to make some effort to make sure that those libraries safely wrapped those native functions. But of course, that's not the end of it. Now we have buttons. We probably want some math libraries. Maybe we want some XML. We want to render some PDF. There's sort of this unending demand for new and interesting code that we can access from inside this environment. Now, we don't have to be stuck in this model. I mean, one of the things that eventually happened with windowing in Java is we said, well, we don't have to actually use all these native libraries. It would be nice if we had some consistent implementation that was pure Java. And so maybe after 10 years, we got the Swing toolkit for Java that said we're just going to we're going to rewrite the whole stack, the whole graphic stack, including how we draw buttons and where we put the pixels, write all that stuff in Java. And now that all that code runs inside the container. And now that it's running inside the container, it's not part of our trusted computing base anymore. So we're not sort of making our environment worse. But that took a long time to do that for one of the most important libraries in Java. And there's this sort of unending pressure to keep adding these other class libraries, these other bits of native code. And so that desire for more variety and more enhancement is outpacing our ability to rewrite code in one of these type-safe languages so that it can belong inside the container rather than contributing to the trusted computing base. So this picture looks exactly the same. You might say, oh, well, Java, that was then, this is now, we got JavaScript now. JavaScript looks more or less the same. The JavaScript container, again, has a pretty simple specification. It's actually not a horrible language. You can write an interpreter for it and be pretty confident you have it correct. But you can't do much with your JavaScript interpreter unless it has access to all this other support functionality, CSS and JPEG and movie decoding and XML, and the list goes on and on. In fact, that list is essentially your web browser. The JavaScript interpreter is, a pretty small component, but the browser itself is 100 megabytes of interesting stuff that your JavaScript code eventually has access to. So it's got we have the same problem, the same structural problem that we're trying to add, that our clever type safety is being undermined by all of these escape valves to other code. So I might propose to you humbly that why don't we take all of this interesting native code, all these interesting libraries, and run them inside some sort of container. Now, when I described Swing, the problem was that we had to rewrite all these things in a type-safe language. So I'm going to have to change that assumption. Why don't we take all this code and run it against, just run it as native code, and we'll just run it in an address space and let the memory management unit of the processor isolate it. That should work out fine, right? We'll just send some native code down to the client. Now, those of you who've been following this field for, since the 90s will say, oh yeah, we've seen that before, Howell. That was called ActiveX, and that did not work out so well. In ActiveX, we sent code down to the browser, and that code could kind of do anything it wanted. It could call into the graphics libraries and networking libraries of Windows, and that turned out to be kind of a disaster. But that's not the same story. ActiveX did not make any reasonable attempt to do isolation. ActiveX was actually saying, we want to give these programs access to the underlying host. We'll sort of punt on security and just sort of hope you only download ActiveX from trustworthy places. That was, in fact, a very bad idea. But that doesn't mean that sending down native code is a bad idea or difficult to isolate. So a few years ago, we wanted to kind of get just start at this idea to show this was even feasible with a project called Zax. And in Zax, what we did is we made a little container that could run isolated code, run native code and isolate it. And we just kind of glued that onto the side of a web browser. And we showed that you could run interesting stacks of libraries in it, things like PDF renderer, Python interpreter, OpenGL. Now, that kind of starts to show that this might be plausible. But it has a couple of limitations. One is we didn't get very far up the stack. We showed some interesting libraries, but not rich interactive applications as we had in mind. But more importantly, we didn't really show anything about the proposed security benefit, because what I'm kind of describing in this talk is taking that really rich web browser and throwing away almost all of it, taking all the complexity and stuffing it inside the container. And in Zax, we didn't do that. We just sort of glued this thing onto the side of a web browser. So that thesis of replacing the complexity of a web browser with a really tiny runtime environment and putting all that complexity inside the applications, making it the vendor's responsibilities, that's the premise of our embassies paper that we presented at NSDI this year. That's not what I'm trying to cover in this talk, but that is the motivation for this talk. That's why it's interesting to be able to take these rich applications and package them against this tiny container. But for this to be a compelling story, we have to, what happens to all the cool stuff we have on the web? What happens to Google Docs and Hotmail and all these rich applications? We need to be able to still run rich and interesting applications that are as cool as the stuff that we have on the web now. So that's what I'm focusing on this talk, is the practical concern of how do we port these applications. So what I'm talking about is being able to take something like KDE's Marble application and run that in this really native environment where we're just sending this down as a binary program. So this is actually running right now, in the environment that I'm about to show you. In fact, let me come back to the talk. Another good example is something like the Inkscape graphics editor, which is actually what I wrote this talk in, and you're actually looking at the talk in Inkscape right now. So I'm presenting it inside this narrow container. So if you have any doubt that this actually works, I'm showing it to you right now. So I'm convincing you that we're trying to run these rich applications, but let me show you that the hard part of the problem is we're trying to run them in this really narrow environment. So in a single slide, with small text, I'll cram it all in, I'm going to show you how narrow this environment is. What is involved in our Picoprocess, in our little microkernel-like environment? Well, as I said, we're going to send native code down, and that code's going to run in an address space on the native hardware. Pardon me. And so what can you do? Well, if you want to run your Turing-complete program, you're going to need to be able to allocate some memory and free it. And our interface is so simple that you can't even decide where that memory goes in your address space. You can just say, I need this much memory, and the host says, here's where it goes. You can create an exit thread so you can access multicore. You get a primitive called a zootex, which is based on the futex in Linux, which is the most minimal primitive we could find for coordinating synchronization with the host's scheduling. So the idea is, I've got a bunch of threads, but I don't need them all to be busy, so I want to tell the kernel when I need them running. And finally, you can interact with real time. You can find out you can look at the real-time clock, and you can set a timer at some point in the future to wake you up. Those basic primitives are enough to run a lot of interesting code, but of course, we want to interact with the world. So all of the interactions from an embassies program with other programs on the same machine or with anywhere outside in the world go through IP, as in Internet Protocol. That's the only IPC mechanism. So you can get your addresses, you can allocate a packet and send one, or you can receive a packet and free it. Why is this a good idea? Because it's really, really minimal. The burden on the host is really small. I mean, anybody can write an IP router, right? I mean, IP routers don't even, you can drop packets, you can corrupt them. So again, the goal is to put a very small burden on the host and make the application sort out the rest. Now, if the only thing we have is IP, then how does our application get privacy and integrity? Well, it needs to do that using crypto. So if you want to build up things like TLS, you need some basic primitives like the ability to get randomness. Now, finally, the reason we're sending this application down to the client is we're trying to get close to the user's display. And so for that, we need to be able to receive keystrokes and clicks, and we need to be able to draw on the screen. But again, we're trying to get rid of all that complexity of CSS and DOM and all that. So the only way you draw on the screen in this world is that your application is given some rectangle of the screen, and you can delegate that to other applications. But if you've got a chunk of the screen that you want to draw on, the way you do that is you allocate your own memory, you draw on an off-screen bitmap using whatever fancy libraries you want, and then you tell the host, I'd like to copy this rectangle onto the display. So again, the only thing the host has to do is know how to copy pixels. So look at this entire interface, and you can see it's actually got a very simple specification. Kind of like building a JVM, it's pretty easy to see how you might build it. In fact, you can write one of these things in a couple of weeks. I've written a few of them, and one of them only took a couple of weeks to write. More importantly than how quickly it takes to write them, the point is that because it's so simple, you can see how to make it correct. You can see that we can get isolation right. This is nowhere near as complex as a browser or as a conventional host operating system. So now we want to run cool applications on top of it. So let's go take a look at an application. Here's the Gimp photo editing app, and it's sitting on top of a bunch of shared libraries, and they don't all fit on the screen, so I'll just zoom out here and put some more on them on the screen. And actually, let me keep zooming out, because there's a really big stack of software there. There are actually 55 shared libraries in the stack of software that runs Gimp. And so if you look at this big stack of libraries, it's sitting on some graphics libraries and then on down the stack. And at the bottom, shown in red, are the glibc libraries. And those are the ones that make system calls to what they're expecting to be Linux, to the POSIX API, which is this 300 system call wide, it's not actually 20,000, it's something like 300, call wide system call interface. So you might look at this and say, wow, that's interesting, Howell. We're going to take these applications that are expecting this rich stack of software and this rich interface, and we're going to change them and run them on this really narrow interface. That sounds like it's going to be pretty invasive and that we're going to have to tweak these libraries a lot. There are two things that save us, make this task a lot easier than you might have expected. The first is that these real applications, real desktop apps like the one I'm showing you right now, they don't actually use very much of that ABI. There's a surprisingly big chunk of it that they actually don't even attend to. And the second thing is, the remainder isn't all that hard to emulate. So rather than modify the applications in place, we can put in an emulation layer to emulate what's left of the POSIX API, and we don't have to be very invasive in how we modify the apps. So let me show you what that emulator looks like. This orange boundary here is the emulator I'm going to describe. So here we are. We've got the emulator sitting in the bottom of an otherwise empty address space. The most important feature in the emulator is this POSIX API interface, that squiggly line. That's the interface that we're going to emulate, and we'll run the software on top of that. And so what's under there is kind of the things that you might expect. File system calls on various virtual file systems. We have a read-only file system you can fetch your binaries out of. We have read-write file system for storing temporary files. All the things you'd expect in a POSIX API, like poll and select and timer calls and things like that. And so this inside the emulator, this is structured with some internal interfaces, as you might imagine. But of course, at the very bottom, what needs to happen is the only way we can actually interact with the world is through that narrow embassies interface. So for example, pardon me. So for example, we have this narrow timer interface where the only thing you can do in embassies is set one timer at some point in the future. But you might have a bunch of threads in POSIX, and they might be selecting on things with different timeouts and have different alarms and so on. And so we have to multiplex that narrow interface to provide the richness of the POSIX interface. A better example is the only interaction for communication is IP. So we get this IP interface at the bottom, and from the point of view of POSIX, if an application says, oh, I'd like to talk UDP, we can create a socket in POSIX, and that thing goes out over IP. Or, for example, I told you we had this read-only file system. We run our own protocol to talk to a cache to load content, and we use that over IP. And then once we pull that content into the address space, we can use that to satisfy read requests on the read-only file system. So that's the basic structure of the emulator. Now, once we have something that looks like POSIX, we want to run these ELF binaries that are meant to be run on something more like Linux. So the way we do that is we pull in Linux's shared library loader, and we put a copy of that right inside the emulator. But it's expecting to talk to Linux, so we just plug it into the top of that POSIX interface. And then we call it, and we say, hey, it would be really nice if you could go load the application called Gimp. And so it talks to the read-only file system and says, where can I get the binary? Maps that binary into our address space, looks at the binary and says, oh, I see it depends on a bunch of other shared libraries, does the same exercise again, and finds those shared libraries in the read-only file system, maps them in the address space. We keep doing this until we've got the loader just keeps doing this until it's got the whole program mapped into memory. Now, at the very bottom of the stack, again in red, are these glibc libraries. Those libraries are expecting to make system calls, so we have to patch them. So that instead of making system calls, they make function calls into our POSIX emulator. But once we've done that, now we've got this structure in memory that's ready to execute, except that it's hooked up to our POSIX emulator rather than to conventional Linux system calls. So now once we start running it, that stack of software itself starts making POSIX calls, doing things like allocating heap memory or creating new threads, and sort of creating new thread turns into embassies calls for allocating more memory for a stack and things like that. So now our address space is sort of filling up, and Gimp is happily running along, thinking that it's running on Linux, even though it's running on this emulator. Now, you might look at this and say, well, that's very nice, John. You drew a block diagram with lots of pieces in it. What all is hiding in there? Maybe this is, you've just rebuilt all of Linux. Two answers to that. The first answer is, please go look at the paper, because I tried to be exhaustive in the paper to convince you that this is actually everything we had to do. So the story is not nearly that bad. But at a high-level view, let me just hop over to this spreadsheet to give you a view of the number of system calls we really needed to worry about. Now, I've left a bug in this spreadsheet so I could convince you that I'm really running the spreadsheet live, so there I updated the graph. But of course, the content of the spreadsheet's, again, running in that narrow interface. The contents of the spreadsheet here is that there are these 333 system calls in Linux. And if you look at this pie chart, something like 2/3 of them are never even mentioned by desktop applications. They're just not even relevant. Of the remaining 100, half of those we can handle in really trivial ways. We can return a 0 or return a -1, and the app works just fine. The intuition behind that is that for a bunch of those system calls, there are things like applications or libraries providing advice to the operating system, and since we're the operating system, we're free to just ignore that advice if it's not relevant. Errors often work because libraries will say, hey, can I use this subsystem over here? And if we say, no, I don't have it, the library happily says, oh, that's fine, I'll go use this subsystem over here, and then we can implement that one. So it turns out that we only have to implement a pretty small subset of the POSIX API. And so you can kind of see some of the stuff in this column here. It's, it's calls on file system interfaces and the ability to create pipes and so on. But it's nowhere near the complexity you might have imagined. So even though I kind of summarized everything with this block diagram, part of the premise here is that this isn't as overwhelming as you might be concerned. So let's take a step back now, go back to this graph with Gimp and look at this big tall stack of software and ask, okay, so now we've got our emulator. How much do we actually have to modify these libraries? How invasive was this to the application itself? So I've color-coded the little ovals in this diagram according to how much we had to modify them. And white means we are literally not touching them at all. That's a binary right off of a standard Debian installation. So the only exceptions are at the very top of the stack is the original application binary, that's the Gimp app. That thing we had to relink. We don't have to do any semantic modifications. We have to relink it with the position-independent flag, because as I mentioned earlier, in the embassies environment, you don't get to decide where your program goes in memory, so we have to make sure that it's position independent, so we can load it anywhere. That's a pretty easy change to make to any application. And then again, at the bottom of the stack are the glibc libraries, the ones that have system calls in them. So we had to apply a static rewriter to turn each of those system calls into a function call. And we could do that once for the glibc suite, and that works for all of the applications. So the moral of the story here is that the emulation is actually almost everything we need. It's a pretty non-invasive approach, and it lets us make our way pretty far up the stack and run these rich applications. So one other technique I'd like to show you is this technique called zones. So here's our address space again with the Gimp running in it. Let me shrink the emulator down here and get it out of the way. And then let me take all of the shared libraries that represent the Gimp and kind of just bundle them together into one oval. Now, the problem we're trying to solve is that Gimp is expecting, on top of this big stack of libraries, is expecting to talk to an X Windows server. But we don't want to communicate out to a big shared X Windows server because that X Windows server is big and complicated and hairy. We have this very narrow interface. We're supposed to paint our own windows and then and blit those pixels right onto the screen. So we want to treat X as a library. Now, we could have gone and rebuilt X as a library, and maybe in the long run that's the right thing to do. But we found that it was nice and expedient to say, well, let's take an X server, the entire program, which is expecting to run in its own address space, and just load it right into this address space, and just treat it as a library. It turns out that because these programs don't have any control of their memory layout, it's fine to just call another copy of the shared library loader and just pull another app into memory. And these apps end up interleaving in memory, not even knowing the other one's there. Obviously, we don't have fault protection between the components, but that's fine because we're trying to treat them as libraries. So now the X is now running in the same process. And this is, by the way, taking a step out. I'm showing you Gimp here, but the presentation is in the Inkscape program. That's exactly what's happening inside this container that you're looking at on the screen here. The application is sitting on top of a stack of software that's expecting to talk to X over a named pipe. Of course, that named pipe is being handled by the emulator, so it becomes an inter-thread communication. And so now they're just going ahead and communicating inside the process. In fact, because we're eliminating some system calls, this sometimes actually speeds up the applications. So we apply the same technique for things like window managers and a dbus component that a lot of applications expect. Again, it's kind of an expedient. Things like dbus, there's a question of whether they even make sense in this environment. Maybe we actually want to rip them out, but the easiest way to neuter that component was to just include a copy of it right inside the app. We also found that it was a handy technique for writing our own programs, because the code that we wrote down in the emulator is kind of ugly because it's sitting down below the POSIX interface, and that means it's below libc. So if we wanted to write a program that would launch all these zones, we could write that in its own zone, because then we could just compile it with GCC, and it uses libc, and everything is kind of comfortable and familiar. So we use that same technique for writing the program that actually coordinates these applications, these programs together to form one application. The other thing that's nice about the zone model is that it's a nice place to package in other libraries. So for example, the LWIP library includes a TCP stack, which is easy to link into one of these zone components. So once we get started, we link that app in, that TCP library in, and it attaches itself down into the emulator. So now when a process comes along, when a program comes along and says, oh, I'd like to do an HTTP session, and so it makes a POSIX call and says, I'd like a TCP stream, please. And the emulator says, oh, I don't do TCP, but oh, I have this hook, and I'll make this callback, and I'll let LWIP handle it. So this gives you kind of a high-level view of how we piece together these coarse components into one big application. All right, so that's kind of the high-level view. And here are the three things I'd like you to take away from this talk. The first is that this technique, which hopefully you were skeptical about when we started, actually really works for real applications. It works for GNU Cache, it works for Gimp, it works for Inkscape, it works for word processor and spreadsheet, it works for a web browser, it works for WebKit, which helps support our premise that we can turn the web browser inside out, because we can take a web browser and stuff it inside this container, and it works for that cool spinning marbly globe. The point is it's pretty general, and it works in a fairly non-invasive way. So it's pretty easy to imagine that's it'll work pretty broadly with additional development effort. And another observation is that the emulation isn't overwhelming. We didn't have to rebuild all of Linux. In fact, we only had to build a pretty tiny slice of it. And that's just because a lot of the complexity in Linux is just not relevant for these applications. They actually use a fairly narrow subset of the POSIX ABI. The final thing I'd like you to take away from this talk is that you don't even have to rebuild those 50 system calls. We took this code and we posted it with an Apache 2 license on the web. And really, if you can think of something cool to do with it, if you want to try to deliver these applications as web components or build a web plugin, really would love to see that happen. I'd love to help out with that. And so the code is out there. The code is in a pretty rough state, so if you decide to go after that, please, by all means, email me. I'm very happy to help and kind of get through some of the early hurdles. So that's the basic talk. Happy to take some questions.
Gone from Microsoft. I have two questions. One is, you haven't shown the overhead of doing emulation in your system, so I'm curious about that.
Yeah, so it's a reasonable question because I gave you this talk, and every time I push advance, the slides kind of ooze on the screen.
Right.
That's not actually the emulator. It's because I really love my really light netbook, and it's pretty underperformant. It actually performs equally awfully natively. Inkscape does. Mm-hmm. But actually, the emulation overhead is not bad at all. It's generally unnoticeable. In fact, in some cases, it actually goes faster because of the fact that we cut out system calls when we're doing stuff inside the process. Kind of the big place performance is a concern is bootstrapping these apps, because you've got this 100 meg app, and you got to get it into the address space quickly. And we have I guess it was a paper in submission that you can look at for how we make that go really fast. And the MSC's paper has a short summary of that. Essentially, what we have to do is, because we're trying to make that host as lean as we can, we don't have the shared buffer cache or the shared object cache in a browser, and we have to replace those functions in a way that is sort of adversary resistant. But it's actually tractable. You can make these things start in 100 milliseconds.
Okay, thanks.
Yeah.
The second question is that you worked on JAX, Embassy, and POSIX compliant Picoprocess. So what is next?
What is next? I'm not sure what I'm going to do with it next. If other people have ideas, we'll talk about it. But kind of the vision is that I'd like to, I mean, Embassy is kind of proof of concept. It says, we can probably get rid of the browser. At this point, there's a bunch of engineering, to kind of clean it up, make it really usable, make it well packaged and something that developers can actually tolerate. But I think with some of that engineering, I think it's actually a practical reality to start shipping apps this way. I think the next step is delivering apps. I mean, right now, there's a lot of cool apps on the web that are being built in JavaScript. Google Docs is kind of a tour de force of JavaScript hacking. But why? Right? I mean, we should be shipping, numeric or Excel, and we should be shipping binary apps as the way we deliver cool apps on the web. And so I think that all the pieces are there now. I think we've gone through a bunch of the research. We know how to build it now, and so now there's a matter of just engineering it.
Thanks.
Thanks.
Hi, Steve Ko from SUNY Buffalo. This is again really interesting work. I was just wondering, this might be just a clarification question. I was just wondering what your target isolation scenario is. So if you're going back to your motivation, if you're just talking about running something over the browser, then wouldn't it be enough to just create a process and assign a different user ID and it creates a separate, isolated environment? Wouldn't it be enough to just do that?
So that's a good start. And but frankly, I don't really believe that Linux or Windows successfully isolates users from one another. They're just too complex. So the first step, I think, is to use a stronger isolation mechanism. I mean, you can use a conventional operating system in a conventional browser and then deliver these apps alongside that world with a stronger isolation mechanism, one that cuts the app off from any conventional system calls and instead replaces them with this interface. That's actually pretty practical, and it would be very secure. But ultimately, the next step after that is if I can start delivering all the CSS and DOM and all the stuff that goes in the browser, then I'd kind of like to get rid of the browser because the browser is complexity and risk. In the end game is if we think about something like the Chromebook, right, where you open this device up and the device is supposed to have no state and no risk, and you just go visit these different websites. Well, it's a nice idea, but again, I don't really trust a Chromebook because the operating system is enormous and sort of possibly porous. But with this model, the part on the client, the only sort of core that everybody has to trust, it could be 100 kilobytes. It could be really small, and really secure, really easy to reason about.
Okay, thank you.
Yeah.
Norman Wilson, University of Toronto.
Okay.
It seems to me we have to be careful not to fool ourselves. My first thought when I saw the zones was, and the idea of you move the X server inside is, but that means that suspect code that the browser is running can get at the X server, and gee, it becomes easy to have a keystroke logger. And then it occurred to me that you're using the keyboard to type at the web browser, and so no matter how you isolate the browser, it's possible for malicious code that's somehow in the browser to log keystrokes. So I think this is good work. I think it's actually very neat work, and I'm genetically inclined to be very happy about the idea of narrowing the interface. But let's be careful to remember where the limits are.
Yeah, so it's a reasonable question. I think because the scope of this talk, I couldn't actually give you a more complete story about how the security model fits together. But the reason the X server isn't a threat here is the X server is in the same trust domain as the app. And so if you're running Inkscape from the inkscape.org site and you're running an email app from an email site, those each have their own X server. At that point, if one of them compromises its own X server and runs a keystroke logger, it can see its own keystrokes. The only place that the keystroke logger is a threat is if I can modify it down in the host. Right? If I can modify the host and see everybody's keystrokes. And so the whole premise behind this is make the host so small that we can reason about it, we can make it sort of very resistant to attack. So the whole point of this is that we've arranged the environment so we have to do as little as we possibly can in the host.
Yeah, or to put it another way, putting the X server in with the browser doesn't make things any worse than the browser can make it, and
I think
so there's still substantial isolation from other things going on the machine.
Part of the problem is that when you think browser, you're thinking of you're bringing with it the intuition about today's browser that the browser is an access control mechanism that is supposed to isolate different pieces up from each other. In this world, there's the host, this very narrow host, that's the only one with an isolation job. And then everything that's left of the browser is really just rendering code. So if you go to 5 different sites and 4 of them send you Firefox and 1 of them sends you Chrome, that's just a big stack of rendering software. At that point, it doesn't matter what happens to that software because its isolation function has been stripped out. And the only function it has is a bunch of rendering components, CSS and all this other stuff.
So yeah, so the problem is thinking of the browser as a universal access mechanism, and therefore there's only one of them.
That's right. Yeah. Now we're separating the role of this rendering stack from the role of the isolation, so we can get the isolation right. Thanks.
Thank you.
I think he was waiting.
Hi, I'm Kostas from the University of Rochester. I was wondering, are these zones increasing? Are the Picoprocesses increasing the memory footprint of what I consider a process in my system? As you start including multiple processes to build one. So how does it look like compared to the original system?
Yeah, so there's some memory cost. So for example, if we take Inkscape and we throw in an X server, we pay something like 10 megabytes to throw, of memory to throw that in there. But the bigger cost is the fact that now we're running Inkscape, it's this 100 megabyte thing, whereas we're not, instead of running some few megabytes of JavaScript on top of a shared 100 megabyte browser. So there's definitely, the high order bit is, I'm happy to spend a bunch of cheap memory if I can make isolation work better. But the next bit is, we can do a bunch of sharing. If we have apps that run on top of similar stacks, we can detect that in a way that doesn't violate the isolation. We can say, oh, we can run those same bits over here as long as they're the bits that I really wanted. I can check that they're the correct content. And then it doesn't matter if I'm sharing the pages with other applications. So it does have an upfront memory cost, but I think using sort of standard techniques and the right layering, we can reduce those costs without undoing our isolation benefits.
All right.
Thanks.
So, from the point of view of having written research operating systems myself, writing the emulation layer for POSIX stuff one way or another isn't that complicated. The problem is getting it to perform adequately. And my concern about this, first concern about this would be that a lot of applications just aren't going to go fast enough. So how well does it perform? Did I miss something that you said about that?
Yeah, so I answered the first question. If you saw the talk, kind of drooling on the screen, that performance is because I'm running a crummy netbook, and it looks just as bad natively. But the higher order bit is that actually in this model, the performance is pretty comparable. We don't notice significant distinctions. In many cases, for example, if we do POSIX on top of microkernels, a lot of times the way we arrange that in past systems has been that every system call, every POSIX call becomes an IPC call, right, and that ends up being very costly. This model's turned inside out. So here, the POSIX emulation, those calls are all inside the process and generally faster. Although I mean, again, it depends on the source of, sorry, Chris said, we're focusing on interactive apps where this isn't a high burden. But actually, when we're CPU bound, if we're stuck inside the address space, it runs just as fast as natively.
Well, the first thing I'd be worried about is like video.
Oh, so now you're talking about the GPU. So that opens up another can of worms.
Yeah.
Right.
Well,
so CPU stuff, anything we can do on the CPU looks about as fast. The video is a concern for 2 reasons. One is the bandwidth of pixels to the display. And I think that's actually not difficult to manage. The other thing is, can we exploit a GPU? And that's kind of another can of worms, but the short story is, I want to treat GPUs like a CPU. I want to, if we can protect the memory in a GPU, then fine. You bring, not only do you send down your app, you send down the stinking NVIDIA driver, you compile all of your own CUDA code down to whatever the architecture is, and you send that, just like you send binary to the x86, you send binary over to the GPU, we isolate it the same way, so we have a similar isolation story. This is a pie in the sky, or it's kind of a longer term vision, but I think it's actually practical. I think GPUs can do this. Thanks.
Yes. Hi, Konrad Miller from Karlsruhe. I actually really like your work. The thing that, not problem that I have with the question that I have is, how do you handle deliberate sharing between applications? Like, applications calling each other or sharing clipboard or
Yep.
sharing files even. How do you solve the specification problem, what is allowed and what is not?
Yeah, that is a fantastic question. It's kind of maybe the most interesting philosophical question about this approach. Please go read the Embassies paper, because that is sort of the place where we try to discuss that in the most detail. But the kind of abstract answer is that one of the things we're trying to do here is shift that responsibility from the IATF defining a web browser that defines how all these things interact out to the vendors themselves. So the model is when vendors write server-side code out on the internet, they interact, they use IP. They come up with protocols and they talk to each other. And the nice thing about running protocols is that if we come up with a new protocol and a bunch of people use it and it turns out to be a stupid idea, any random site on the internet can say, that's a bad idea, I'm not going to run that thing. This contrasts with what we usually do on desktops, where we have some platform, like we have Windows or we have a browser, and we decide on a new sharing mode, and we put it in there, and everybody gets it whether they like it or not. And if it turns out to cause XSS or CSRF, well, too bad, dude. It's your problem now. So those are kind of two different models. And so what we're trying to do here is shift the evolutionary model to this server-side model. So I told you that the only interaction mode you have is IP. The idea is that now, sort of from an evolutionary standpoint, these applications can evolve exactly the same way they do on the server. So if you're Amazon, you write a bunch of server code, you decide what web browser or what web server and Python and PHP, whatever you're going to run on your server, and you decide what's going to run on the client. You say, oh, we're going to use Firefox modified with some hacks, and it's going to have these hooks, and then that stack of software that you use will speak some protocols. It can talk a clipboard protocol, it can talk whatever other protocols, printing, internet printing protocol, whatever it wants to speak, and so we're going to re-evolve these communications as protocols, but the reason, we can now go back and build everything we have in the browser today, but the important thing is maybe that's a stupid idea, and now we can deviate away from that. So individual vendors can say, yeah, this is all fine except for that, having somebody post a form over to me and having me send my cookies in automatically with that form, that's a stupid idea. We're just going to turn that off. So it's a very abstract answer. I'm not answering concretely what happens to individual protocols, although we do in the Embassies paper, but the abstract answer is, we're going to shift the way we think about those interactions.
Thank you.
Thanks.
Let's thank all three speakers now.